10.9 Rolling motion of a rigid object. The outline of this video is as follows. We will begin by introducing rolling motion, which is a common type of motion that combines both translation and rotation. Then, we will define the specific condition for pure rolling, which occurs when an object rolls without slipping. Next, we will analyze the velocity of different points on a rolling object by adding its translational and rotational velocity components together. Following that, we will apply these ideas to the important case of an object rolling down an inclined plane, using energy conservation to solve for its motion. To conclude, we will work through several examples to help reinforce these key concepts. Let us begin our study of rolling motion, which is a fundamental combination of translational and rotational movement. To see why this can seem complicated, imagine tracking a single point on the outer edge of a rolling wheel. As the wheel moves forward, that point traces a looping path through space. This specific curve is called a cycloid, and analyzing its motion directly would be quite challenging. Fortunately, there is a much simpler way to describe the object's overall movement. Instead of focusing on a point on the rim, we can track the object's center of mass. For a wheel or cylinder rolling along a flat surface, the center of mass travels in a simple, straight line. By separating the complex motion of the rim from the simple motion of the center, we can build a clear physical model. Therefore, our analysis of rolling objects will start by focusing on the straight line motion of the center of mass. To analyze objects that roll without slipping, we need a simple but powerful relationship connecting their linear and rotational motion. This scenario is called pure rolling motion. Imagine a wheel of radius r. As it rotates through an angle theta, the distance its center moves forward, ts, must exactly match the arc length along its edge. This gives us the geometric condition, s equals r times theta. From this starting point, we can find the velocity and acceleration. By taking the time derivative, we find that the translational speed of the center of mass, written as v(c)m, is equal to the radius r multiplied by the angular speed, omega. Taking the derivative one more time shows that the linear acceleration of the center of mass, acm, is equal to r times the angular acceleration, alpha. Be careful not to confuse this with a similar-looking formula. The equation v(c)m equals r omega gives the translational speed of the entire object. The other formula, v tangential equals r omega, gives the speed of a single point on the rim relative to the center. For any object rolling without slipping, its center of mass speed is its angular speed multiplied by its radius. We can understand the velocity of any point on a rolling object by modeling its motion as a combination of pure translation and pure rotation. The key idea is that the velocity of any point is the vector sum of two separate components, the translational velocity of the center of mass and the rotational velocity of that point about the center of mass. Let us apply this to a wheel that is rolling without slipping. First, every point on the wheel is moving forward with the translational velocity of the center of mass, which we call v(c)m. Second, every point is also rotating around the center. For a point at the very top of the wheel, its rotational velocity is in the same direction as the translations. These two velocities add together, so the top of the wheel moves at 2 times, v(c)m. At the center of the wheel there is only the translational velocity, v(c)m. At the bottom, where the wheel touches the ground, the translational velocity is forward, but the rotational velocity is backward. Since they have equal magnitudes for pure rolling, they cancel out, and the velocity is 0. The essential result is that the point of contact with the ground is momentarily at rest, while the top of the object moves twice as fast as its center. We can determine the total kinetic energy of a rolling object by viewing its motion in a specific way. Since the point of contact with the ground is instantaneously at rest, we can model the object at that instant as if it were purely rotating about that contact point, which we will call P. The kinetic energy for this rotation is K equals 1/2 I sub P times omega squared, where I sub P is the moment of inertia about the axis passing through P. To make this equation more practical, we can use the parallel axis theorem. This theorem relates the moment of inertia about point P to the moment of inertia about the center of mass, I sub Cm. It tells us that I sub P equals I sub C m plus m times r squared. Substituting this into our energy equation and distributing the terms gives us two distinct parts. Using the fact that the center of mass speed, Vcm, equals r times omega for pure rolling, we find a powerful result. The total kinetic energy of a rolling object is the sum of its rotational kinetic energy about the center of mass and the translational kinetic energy of its center of mass. Let us analyze the motion of an object rolling down an incline, which is a classic physics problem. To understand this scenario, we must consider the role of friction. For an object released from rest to start rolling, it needs an angular acceleration. This requires a net torque about its center of mass. The only force that can provide this torque is the static friction force between the object and the surface of the incline. Now here is the key insight. Even though a friction force is acting, it does no work on the object. This is because we are considering the case of rolling without slipping. In this situation, the point on the object that touches the incline is momentarily at rest relative to the surface. Since work is force times the distance over which it acts, and the point of application of the static friction force does not move, the work done is 0. Therefore, because this essential friction force is non-dissipative, the total mechanical energy of the object Earth system is conserved. Let us use the principle of energy conservation to find a general formula for the final speed of any object rolling down an incline. First, we can combine the rotational and translational parts of the kinetic energy into a single expression. By substituting the angular velocity with Vcm over r, we can factor out the center of mass velocity squared. This gives us the total kinetic energy, K equals 1/2 times the quantity Icm over r squared plus m, all multiplied by Vcm squared. Next, we apply conservation of energy. AAT, the top of the incline. The object starts from rest, so its energy is purely gravitational potential energy, given by m times g times h. As it rolls to the bottom, this potential energy is completely converted into the total kinetic energy. By setting the initial potential energy equal to the final kinetic energy, we get a direct relationship between the starting height and the final speed. Finally, solving this energy balance equation for the center of mass velocity gives us a powerful result. The final speed, Vcm, equals the square root of the fraction 2 gh divided by the quantity 1 plus the ratio Icm over m r squared. This single equation allows us to calculate the final speed for any rolling object. Let us apply our understanding of rolling motion to a classic conceptual question. We have a ball rolling down one incline and a box sliding down an identical but frictionless incline. Which one gets to the bottom first? To answer this, we need to think about energy conservation. Both the ball and the box start with the same amount of gravitational potential energy. For the sliding box, all of this initial potential energy is converted into translational kinetic energy, which determines its speed down the ramp. The rolling ball is different. its initial potential energy is converted into two forms of energy: translational kinetic energy and rotational kinetic energy. Because some of the initial energy must be used to make the ball spin, there is less energy available to increase its translational speed. As a result, the box will always have a greater translational speed than the ball at any given height. Therefore, the box moves faster down the incline and arrives at the bottom first. Now we will solve this problem for the specific case of a solid, uniform sphere. The key is to substitute the correct moment of inertia for a solid sphere into the general speed equation we just derived. From a standard table, the moment of inertia for a solid sphere about its center of mass, ICM, is 2/5 mr squared. When we look at the term ICM divided by mr squared in our speed equation, the r squared parts cancel out, leaving just the fraction 2/5. The denominator in our main expression then becomes 1 plus 2/5, or 7/5. This gives a final speed for the center of mass equal to the square root of the quantity 2gh divided by 7/5. Simplifying this fraction gives us the square root of 10/7 gh. Notice that this speed is less than the square root of 2gh, which is the speed a non-rotating object would have. This is because some of the initial potential energy goes into making the sphere spin, leaving less energy for its translational motion. Now that we have the sphere's final speed from our energy analysis, we can find its acceleration by connecting that result to kinematics. First, we need to relate the vertical drop height, h, to the distance the sphere travels along the incline, x. Using trigonometry, we know that h equals x times the sine of the incline angle, theta. Substituting this into our speed equation gives a new expression. The square of the center of mass speed equals 10/7 times g times x times sine theta. Next, we recall a familiar kinematics equation for constant acceleration from rest. The final speed squared is equal to 2 times the acceleration times the distance. So VCM squared also equals 2 times ACM times x. Since we have two expressions for the same quantity, we can set them equal to each other and solve for the accelerations. The final result is that the acceleration of the center of mass is 5/7 of g sine theta. This is less than the acceleration for an object sliding without friction, because some of the potential energy must become rotational kinetic energy, leaving less to increase the object's translational speed. Now we will apply our energy principles to a classic problem involving a spool rolling without slipping. Our goal is to find the final speed of the spool's center of mass after it has been pulled a distance L. The physical setup is a spool with mass, m, an outer radius r, and a smaller inner axle of radius ARE. A string is wrapped around this inner axle, and we pull it horizontally with a constant tension, T. The most direct way to solve this is by using the work-energy theorem. This theorem states that the net work done on a system equals its change in kinetic energy. In this case, the work done by our pulling force T is what increases the spool's energy. A key insight for rolling motion is that the force of static friction does no work. This is because the point of contact between the spool and the surface is instantaneously at rest, so the force acts over zero displacement. Therefore, the work done by tension is converted entirely into the spool's kinetic energy, which has both translational and rotational components. To find the spool's final speed using the work-energy theorem, we must calculate the net work done on the system and its change in kinetic energy. Let us start with the work done by your hand. This is equal to the force T you apply, multiplied by the total distance your hand moves. This distance is not simply L. As the spool rolls forward a distance L, your hand also pulls an extra length of string that unwinds from the inner axle. The length of this unwound string is the axle radius, r, times the angle of rotation, theta. Because the spool rolls without slipping, this angle theta is equal to L divided by the outer radius, ARE. So the total distance your hand moves is L plus the quantity r times L over ARE. Next, we calculate the change in kinetic energy. Since the spool starts from rest, this is just its final kinetic energy, which has both a translational and a rotational component. We can write the entire expression in terms of the final center of mass speed by using the no-slip condition, where the angular speed omega equals the center of mass speed divided by AR. We now have expressions for both the work done and the change in kinetic energy. To find the unknown friction force, we now switch from an energy-based approach to the impulse momentum theorem. The first equation on the slide is our previous result for the final speed, found using the work-energy theorem. Now for part B, we use a different tool. The impulse momentum theorem states that the net force on an object multiplied by the time interval it acts equals the object's change in momentum. Here, the net horizontal force is the tension T minus the friction force F. This net force, acting over a time interval delta, T, causes the spool's momentum to change from 0 to m times v cm. We can find the time interval using kinematics. Because the spool starts from rest and has constant acceleration, the distance L is equal to the average velocity times time, which gives delta T equals 2 L's divided by v cm. Substituting this expression for time into the impulse momentum equation and rearranging gives us the final expression for the friction force, F. Let us summarize the key results for an object in pure rolling motion. We have seen that this motion is a combination of the translation of the center of mass and rotation about the center of mass. For an object rolling without slipping, these motions are linked by the condition that the center of mass speed, v cm, equals r times the angular speed omega. This leads to the total kinetic energy being the sum of two parts. The translational kinetic energy, 1/2 mv/cm squared, and the rotational kinetic energy, 1/2 I/c/m omega squared. A powerful application of this is analyzing an object rolling down an incline. Since static friction does no work, mechanical energy is conserved. This allows us to find the final speed and acceleration. Importantly, these values depend on how the object's mass is distributed, which is captured by its moment of inertia. The key factor is the ratio of the moment of inertia to the quantity, mr squared. This ratio determines how energy is partitioned between translational and rotational motion. Therefore, the distribution of an object's mass, not just its total mass or radius, determines how fast it rolls. To wrap up, let us test our understanding with a couple of review questions based on the concepts we have just discussed. First, imagine a solid sphere and a hollow cylinder. They have the same mass and the same radius. If you release them from rest at the top of an incline, which one gets to the bottom first? To figure this out, think about how their different moments of inertia affect the way their initial potential energy is converted into translational and rotational kinetic energies. The second question refers back to the example of pulling the spool. We determined that the static friction force pointed to the left, opposing the pull. But could the friction force ever point to the right, in the same direction as the tension? Consider the torques about the center of mass and what is required for the spool to roll to the right without slipping. I encourage you to pause the video here and work through these two scenarios.